Guided exercise number 1. The volume of a sphere of radius r is v equals 4/3 pi r cubed. Part A says determine the volume of the sphere with radius r equals 2 centimeters. Remember to include units here and later. So the volume is 4/3 pi times 2 cubed. And the units for volume are whatever your units are for your radius and then cubed. So centimeters cubed. And if you wanted to, you could simplify this. We do need it later, so we'll go ahead and simplify it. 2 cubed is 8. 8 times 4 is 32. So 32 pi over 3 centimeters cubed. Part B says determine the average rate of change of the volume when the radius changes from r equals 2 centimeters to r equals 4 centimeters. So the average rate of change of the volume uses the volume function. And we're going from r equals 2 to r equals 4. So we'll do v of 4 minus v of 2 all over 4 minus 2. V of 2 we got already. V of 2 is 32 pi over 3. And then V of 4 is 4/3 pi times 4 cubed. 4 cubed is 64 times 4 is 256. So this is 256 pi over 3. All right, so plug that into the average rate of change formula. So 256 pi over 3 minus 32 pi over 3, and then all over 4 minus 2, which is 2. So I used my calculator to simplify the numerator fractions, combining them to get 224 pi over 3, and then that's all over 2. So this is the same thing as 224 pi over 3 times a half, which is 224 pi over 6. And you could leave it that way, but I did realize that I could simplify the fraction a little bit by dividing by 2 on the top and bottom to reduce it to 112 pi over 3. And we definitely need units. So let's go back and think about units. Our volume units are in centimeters cubed. Our 4 and the 2 here represent radii, and their units are centimeters. When you subtract them, you're going to get centimeters again. And so our numerator units are centimeters cubed. Denominator units are centimeters. So when we look at the whole fraction, we're looking at centimeters squared. Part C says calculate dV over dr. Assuming that r is given in centimeters, what are the units for dV over dr? So dV over dr is going to be, use the constant multiple rule, 4/3 pi times, and then the derivative of r cubed is 3r squared. Did you put an r here instead of an x? You should have an r there because your variable that you're differentiating with respect to is r here. So dV over dr simplifies to 4 pi r squared. Assuming that r is given in centimeters, what are the units for dV over dr? They should be square centimeters. And it goes back to the units that we looked at in Part B. The derivative comes from looking at the difference quotient and taking the limit, at least if you do it the long way. And the units for the difference quotient, that does not look like units. The units for the difference quotient are centimeters cubed over centimeters, just like they are in part B. So the units for the difference quotient are centimeters squared, and so they have to be that for the derivative as well. So 4 pi r squared centimeters squared. Part D says determine the instantaneous rate of change of the volume when r equals 2 centimeters. I put the instantaneous in parentheses because it means the same thing regardless of whether or not it's there. So if you just say determine the rate of change, that means determine the instantaneous rate of change. And both of those things mean determine the derivative when r equals 2 centimeters. So we already worked out that dv over dr was 4 pi r squared centimeters squared. And so the instantaneous rate of change when r is 2 centimeters is the derivative with respect to r evaluated at r equals 2, which is 4 pi times 2 squared centimeters squared. And if you wanted to, you could consolidate a little bit. 2 squared is 4, times 4 is 16. So you could write this as 16 pi centimeters squared. Part E says determine d squared v over dr squared. And what that means is the second derivative of the volume function with respect to r. So we're going to use dv over dr again. So dv over dr is 4 pi r squared. And now we need to take a derivative again. So d squared v over dr squared is going to be, use the constant multiple rule, 4 pi times derivative of r squared is 2r. And so our second derivative is 8 pi r. And let's think about the units. So we said that for the first derivative, our units should be centimeters squared. Well, when we differentiate again, in effect, we've built a difference quotient for the derivative. And so we need to think about the difference quotient for the second derivative is going to be centimeters squared over centimeters. So our units for the second derivative have to be centimeters. Now, if you look at the powers of r that you have in both of these expressions, when you have an r squared, it makes sense that your units should be centimeters squared. When you have an r, it makes sense that your units should be centimeters. And so that's another gut check to say, okay, yeah, this definitely does make sense. Part F says fill in the chart below, assuming that r is given in centimeters. What is the pattern with the units? So v has centimeters cubed, dv over dr has centimeters squared, and then d squared v over dr squared has units centimeters. And so the number of centimeters in the units, the number of centimeter products in the units is decreasing by 1 each time we take a derivative. And so if we were to take another derivative, we wouldn't have any units. So d cubed v over dr cubed wouldn't have any units, will it? We would be fresh out of centimeters.